Good morning, this is Dr. Kumar, Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain the power law of fluid flow as a falling film. So this is the power statement. Consider a liquid of density ρ in laminar flow down an inclined flat plate of length L and width W. The fluid flows as a falling film with negligible rippling under the influence of gravity, and effects may be neglected because length and width are large compared to film thickness h. So determine the steady state velocity distribution for a non-Newtonian fluid that obeys the power law model. Example: polymer liquids. Reduce the result to the Newtonian case. Second, obtain the expression for volumetric flow rate for a power law fluid. Simplify it for a Newtonian fluid. Third, what is the force exerted by the fluid on the plate in the flow directions? So if we see the schematic of this particular falling film, so this is an inclined plane, inclined down by theta. So this is a differential volume. The fluid is falling as a thin film. So total thickness of the film is h, and the width of the plate is w, and let's say the length of the plate is L. So the coordinate is chosen on the free surface of the film. So here is the origin on the top. Y coordinate is this side, Z is in the direction of width of the plate, and X direction in the direction of the flow. So in this case, if we apply the x momentum balance, so x momentum balance is given by rho del u upon del t plus mu del u upon del x plus v del u upon del y plus w del u upon del z equal to rho gx minus del p upon del x plus mu del square u upon del x square plus del square u upon del y square plus del square u upon del z square. So here this term is getting cancelled due to steady state flow. Del u upon del x term is getting cancelled, fully doublet flow in direction x. V and w are getting cancelled because no flow in direction y and z. This is due to fully doublet flow. Del u upon del x term is getting cancelled. Now del u upon del y term is always significantly higher than del u upon del z. So from dimensional analysis, by the magnitude wise, this term is significant than this, because width is very large as compared to the thickness of the fluid. So we will end up with finally that 0 equal to rho gx minus del p upon del x plus del upon del y mu del u upon del y. So this we can write as tau yx So here we have this rho gx minus del p upon del x equal to del tau yx upon del y. So here we can write it here. We can integrate tau yx equal to del p dash y plus c1, where del p dash is the modified pressure is minus rho gx plus del p upon del x. This is equation number 1. Boundary condition 1, we have y equal to 0, tau yx equal to 0 at free surface. So free surface cannot have any shear. So for that case, tau yx equal to delta p dash y. So your c1 equal to 0. So now since tau yx equal to mu del u upon del y to the power n for power law fluids, So we can find this. We can find du upon dy equal to delta p dash mu to the power 1 by n y to the power 1 by n. So we can integrate this one. So if you integrate that, you will get u del p dash upon mu 1 by n y to the power 1 by n plus 1 upon 1 by n plus 1 plus constant c2. Now boundary condition is y equal to h, u equal to 0, no slip conditions because plate is fixed. So your c2 comes out to be this one. Now substituting this c2 in equation number 2, so the velocity expressions comes out to be u is minus delta p dash upon mu to the power 1 by n s to the power 1 by n plus 1 upon 1 by n plus 1 bracket 1 minus y upon s to the power 1 by n plus 1. So this is the velocity expression for power law fluid. Now for Newtonian fluids, n equal to 1, so for Newtonian fluid this velocity expression comes out to be minus delta p dash mu h square upon 2 bracket 1 minus y upon h square, where delta p dash is minus rho gx plus del p upon del x, so minus rho g cos theta plus 0. So for Newtonian fluids this is rho g cos theta h square upon 2 mu 1 minus y square upon h square. Now the volumetric flow rate can be that v dot dA, so this v dot dA, so this is area. So we have the expression for velocity, this one multiplied by dA, so dy into dz. So if we'll integrate this expressions for entire gap or thickness of the fluids, so this 0 to h. So here if we integrate that, substitute the limit, arrange it properly, you will end up here this one, that 1 minus 1 upon n plus 2. Then simplify it further, you will end up with q dot equal to minus delta p dash upon mu to the power 1 by n s to the power 1 by n plus 2 w plus n upon 2n plus 1. So this is the expression for volumetric flow rate for power law fluids. For laminar Newtonian fluids, n equal to 1. So for Newtonian fluids, q comes out to be minus delta p dash mu h cube w upon 3. Delta p dash comes out to be minus rho g cos theta, which we can substitute here. So your q comes out to be 1 by 3 rho g cos theta w h cube upon mu. Force on the plate, just calculate the shear stress on the plate, multiply by area. So tau by x into dA. So for that this is expression for velocity. We want shear stress, we can find du upon dy. From here differentiate it, so we will get expression of this, then we can put a power of that, we will get tau by x is equal to this delta p dash y actually. So is delta p dash y, so multiply by this, you will get this one. So at maximum would be at y equal to h. So force on the plate is delta p dash h into wl, where delta p dash is minus rho g cos theta, so that can be substituted here. So the force on the plate would be rho g hwl cos theta. So fluid will try to drag the plate in the direction of the flow. So this is all about the Newtonian, means power law fluid flow as a falling film. Thank you.